Okay, welcome everyone. Thank you all for joining this session where we are very lucky to be joined by Danilo from EPV Technologies. He'll be answering the typical "Is my new machine performing as expected?" question and also walk us through a real case of migrating from Z13 to Z15. As per usual, feel free to leave any questions you have in the chat box as we go along, and Danilo will answer at the end of the presentation. Also, we'd be grateful if you could leave feedback as well using the link that I'm about to paste in the chat box. And if you would like to access the paper of this presentation, then this will be available on the agenda itself, and it's a far more detailed version than the session slides. So with that said, I'm now handing it over to you, Danilo.
Okay, can you hear me?
Yep, I can hear you perfectly.
Okay, so I will do as I did before. Let me start sharing my view. Okay, share screen. Then share computer sounds. Okay, so I will start, and please, Piara, starting from the third slides, if there are problems, you let me know, but I think there should be none.
Sure.
Okay. Okay, good morning to everybody. So this is the title of the next presentation. This is a pre-recorded session. So it means that in a couple of slides, I let it start and it will flow to the end. So there is a long talk. And if you can keep your questions for the end, at the end, we will open the microphones and I will try to answer to eventual questions. So this is the paper. And okay, this is the session 1AG and the link to provide the feedback. So please provide the feedback at the end. Hello and welcome to everybody. My name is Danilo Gipponi and I am the Chief Executive Officer of EPV Technologies. This paper, titled "Is my Z15 performing as expected?" is part of GSC Share UK 2020 and is session 1AG. The paper, or better, the presentation, is based on a white paper by Fabio Massimo Ottaviani, which you can retrieve from the Share site. This is the agenda of this technical presentation. Many of the points covered are methodological, meaning that you can use the suggestions provided every time you need to perform a capacity planning activity. As usual, after an introduction and the theory, we will provide a practical example, the results of a real case. If you are an expert and you haven't yet fixed your coffee, you can do it now while I introduce the object. LSPR benchmarks are provided at every new hardware release, providing an indication of the performance of the new machine comparable with all other hardware existing on the market. Based on this number, customers decide the characteristic of the new machine. In the past, there has been occasions where the promised performance was not delivered, for different reasons. This is why, when the new hardware is installed, you have to verify if the expectations were met or not. We regularly receive requests from some customers to help them evaluate the new machine's performance. Their question is always the same: is my new machine performing as expected? As you can imagine, it also happened with upgrading to Z15. We will try to provide suggestions to help you answer this question. As already told, these suggestions are not specific for an upgrade to Z15. They also apply to any machine upgrade, and in the final part, We will also discuss a real case of migrating from Z13 to Z15. Choosing the right days to compare, it may look like an easy task, but people tend to underestimate the importance of this step. Here are some rules we suggest follow. Example, if your workload is much lighter on weekends and holidays, this day should be excluded from the comparison. And if possible, you should compare days when all the helpers were on the old machine with days when all the helpers are on the new machine. And you should also try to compare peak situations. Because helper migration is normally done in steps, it is likely that you have a certain number of days when your helpers are running on both machines. In such a situation, performance is normally better because there is less competition amongst the helpers, so you should go on with your measuring and not come at conclusions yet. Let us see an example. This graph shows the measurement of the cycle per instruction values of a production helper throughout a migration. This measurement refers always to the old machine, but as you can see, there is a significant increase in performance in this period. Why? Because as soon as other helpers were moved away to the new machine, more resources were available and less competition with other helpers showed its effect. Many companies have workload peaks at the end or at the beginning of the month and a quiet period in the middle. A mistake would be to compare a peak with a quiet period. Comparing peaks with peaks is normally the best solution because performance is much more important during peak times. As an example, in this graph you can note the end of the month peaks in orange, which in this case are even enhanced by some holidays, Easter and the 1st of May. Next chapter is about helper CP consumption. What all customers want to know is if the new machine is providing the expected and planned processing power for both CPU, more important because the cost of the software is related to it, and also zip engines. Depending on the workload characteristics and the adopted software licensing policies, you must decide whether to consider all the hours of the day or only some time shifts in your comparisons. The next two tables show the total cake consumptions, including all the helpers, in normal conditions, not during an upgrade. They are extracted from the daily trend report of the IPv4ZOS product. They provide the CPU consumed in MIPS by helper and the total of the cake in the column with the label used. Using a report like this, it will be very easy to make comparisons between different time periods. You can also focus your analysis just on the production helpers, those highlighted in this example, if for your business they are the most relevant. When planning a new machine capacity, it is very important to minimize the probability of zip-eligible work overflowing to a general-purpose engine. A third check needs to be dedicated to evaluating the variation of the CPU usage due to such overflows. Another task you need to perform is checking the overhead. After an upgrade, it is always good practice to check the PRSM and the internal system overhead. The PRSM overhead can be directly measured, but it is not by far the only overhead you have. The biggest part is included in application CPU consumption and depends on the contention of the processor cache. There is not a direct measurement available for the internal system overhead, but you can evaluate it by looking at the system capture ratio daily trends. We can directly measure two components of the PRSM overhead: the CPU consumed by PRSM to manage the helpers, reported as physical, and the CPU consumed by each helper when talking to PRSM, calculated as the difference between dispatch and effective time. As a rule of thumb, both these measurements should be less than 1%. If the number of helpers and their configuration has not been substantially changed, you should not find meaningful variations in the measured overhead. This standard view, extracted from EPV4ZOS, shows the percentage of CPU wasted or needed to accomplish the various tasks of PRSM. In other words, what is necessary to run the OS before any other workload is even started. The system capture ratio is the ratio between the CPU attributed to all the workloads and the total CPU used. It is an inverted measurement of the system overhead. The lower the value, the higher the overhead. A widely accepted rule of thumb is to consider as acceptable values between 85 and 95% for production helpers. Again, a standard view taken from the product EPV4ZOS that shows the hourly capture ratio values for a specific helper. The next step is to check the performance of critical applications. Another important verification that is needed is the impact of the new hardware on the most relevant applications in terms of throughput and performance. You should focus on the more stable applications, and you should choose an appropriate time shift, for example from 8 to 12 a.m. on working days only. An important thing to consider when comparing the CPU usage is the CPU speed. Depending on the CPU speed, the amount of work which can be processed in one CPU second is different. When you upgrade to a new machine, normally the effect is that the CPU seconds used by your application is reduced, giving the illusion of a reduction in the CPU consumption. To have a meaningful comparison, you need to normalize the CPU seconds. To normalize the CPU seconds to the whole machine, you can use the service unit rate. Here is the formula you should use to normalize CPU seconds. The normalized CPU seconds before and after the upgrade provide a better understanding of the impact of the upgrade. It is years now that IBM provides mainframe counters to understand how your workloads deploy on the machine you are using. This chapter is focused on mainframe counters. The mainframe counters are provided in SMF 113. From those, some useful indexes can be calculated. It's very important that your analysis is not based on a small number of hours. It should consider values measured during the workload peaks and over a long period of time. The cycle per instruction index represents the average number of cycles needed to perform an instruction. It can be calculated by using basic counters, and the formula is in the slide. There is not a rule of thumb for the ideal CPI value. The lower, the better. Cycles per instruction alone can be misleading. To evaluate the performance benefits when moving to a new machine generation, you need to normalize the CPI values to the processor speed to make a meaningful comparison. This because if the CPU speed increases, there are more cycles in a second. Here is the simple formula you have to use. In this table, taken from EPV4ZOS, the cycle per instruction are also split in finite and infinite cycles, where infinite cycles are those needed to execute the program even if the resources would be infinite, whereas the others are those that theoretically could be improved with faster and better technologies. This graph shows the average CPI calculated across the prime shift hours during March working days. As you can see, values are generally between 2.5 and 3. Workload capacity performance is quite sensitive to how deep into the memory hierarchy the processor must go to retrieve the workload's instruction and data to be executed. The higher percentage of level 1 miss and RNI, relative nest intensity, the worse the workload capacity performance will be. The percentage of level 1 miss index represents the percentage of data and instruction which were not found in the level 1 cache. It can be calculated by using basic counters and the simple formula in the slide. The RNI index represents how deep into the memory hierarchy the processor must go to retrieve the instruction and data when a level 1 cache miss occurs. The relative nest intensity (RNI) calculation is much more complex and is dependent on the machine model. Let us know if you need more details to calculate it. This will not be covered specifically in this presentation. Using the percentage of level 1 miss and RNI values, you can understand which benchmark best represents the workload running in each system. The machine will waste more cycles on a workload represented by a high RNI benchmark, thus delivering less capacity. Low RNI means more throughput and better performance. Let's have a look again at the standard view provided with EPV4ZOS. You can note that all the needed indexes are available. If we use the values of the table in the previous slide, the percentage of level 1 miss is always less than 3%, and the RNI is always greater than 0.75. Note that we just used few hours of a specific day. But in this example, our benchmark is average RNI, which by the way is the most common. This graph shows the average percentage of level 1 miss calculated across the prime shift hours during the March working days. You can note that the situation is not as clear as it appears when looking at just few hours. The percentage of level 1 miss is in many days close to 3, and in one day it's even over that. This graph shows the average RNI calculated across the prime shift hours during the March working days of the same system. The RNI values are always higher than 0.75, and in some days are even higher than 1. We can still assume that average RNI is the benchmark that better represents the system workload, but we are very close to the classification limits. So, when looking at a full month, we see that the percentage of level 1 miss gets closer to 3%, and it was over in one day. The RNI is greater than 1 in many days. Is average RNI the benchmark that best represents our workload? You have to monitor this situation. Finally, let's have a look at the real customer experience of a migration from Z13 to Z15. Story. One of our customers migrated from a Z13 to a Z15. In this presentation, we will essentially focus on understanding if the Z15 performs as expected in terms of CPU consumption. We chose the days to make comparison following these rules: excluding weekends and holidays, comparing days when all the helpers were on the old machine with days when all the helpers were on the new machine, and selecting days in the middle of the month. This because the workloads at the beginning and end of January were not the same in March, because there was early stuff running in that period. The days we chose were from 13th to 24th of January before the upgrade, and from 9 to 20 of March after the upgrade. So, 2 weeks before, 2 similar weeks after the upgrade. In our examples, all the hours in the prime shift from 8 to 17 have been considered. In this graph, we compare the average daily CPU utilization in the 2 time periods of the most important production helper. The red lines represent the average percentage of utilization of the whole machine in the 2 time periods. That was 60% of the Z13 and almost 50% of the Z15. You can note that the MIPS used values, blue bars in the graph, in the first Z13 and last Z15 weeks are very similar. The Z13 is targeted at about 90,000 plus MIPS, while the Z15 is targeted at about 22,000 plus MIPS. These targets refer to an average RNI workload. Remember the suggestion to normalize the CPU? If we normalize the Z13 utilization to the Z15 capacity, the expected percentage of utilization of the whole machine becomes 52.7%, while the measured Z15 utilization is 49.4%. It seems that the Z15 is performing slightly better, about 3%. This could be because there are different workloads running in the analyzed time periods, or maybe because the reduced CPU contention, because of a lower percentage of utilization, makes it perform better. Note that application consumption also increases when percentage utilization of the CAC grows. This is mostly due to processor cache contention. It can be estimated between 3 to 5% more every 10% of increase of CAC busy, depending on the workload RNI characteristics. In this specific case, CAC busy decreased by about 10% with z15, consequently explaining a 3% reduction. In this environment, we have three production helpers with the workloads described in the slide. This graph shows the results on the helper named PRD1, an helper running old IMS DB2 applications requiring high performance. As you can see, the consumption with the Z15 are similar or slightly lower. This graph shows the results on PRD2, an helper running new IMS DB2 applications requiring high performance. Again, as you can see, the consumption with the Z15 are similar or slightly lower. This graph shows the results on prod, an helper running mostly DDF and batch workloads. As you can see, performance and consumption appear more erratic for this system. We realized this was due to some very intensive batch activity related to some company activities which normally start at the end of March, but unfortunately for our analysis, they have been anticipated this year. Let us now have a look at the Cpi indexes. Of course, we normalize them. This graph shows the results on PRD1, the helper running old IMS DB2 applications requiring high performance. You can note that the processor cache effectiveness increased. This graph shows the results on PRD2, the helper running new IMS DB2 application requiring high performance. Again, you can note that the processor cache effectiveness increased. This graph shows the results on prod, the helper running mostly DDF and batch workloads. Now you could be surprised to note that the processor cache effectiveness increased. This report could seem contrasting with the CPU utilization reported before. In fact, there is no contrast. The number of cycles to perform an instruction is lower in Z15, but the number of instructions to execute is higher because of the increase on batch workload I mentioned earlier. We analyzed the MS transaction of the most important old applications in the PRD1 system. Without CPU normalization, you can evaluate the performance improvement due to the higher speed of Z15. But after the CPU normalization, you can also evaluate the decrease of the average CPU consumption per transaction. Overall, the application throughput was comparable. The graph shows the average CPU time consumed before and after the migration. This graph shows the normalized average CPU time before and after the migration. This last graph shows the throughput, comparable between the two periods. Overall, we can say that in our case study, the z15 migration has been very successful. It is now time to open the meeting so that everybody can put forward her or his question. The movie will end and I will open the microphone for questions. Okay, that was the presentation. Can you hear me? Chiara, can you confirm?
Yes, I can hear you perfectly.
Okay. Again, if there are any questions, okay then. So please submit your feedback at the link. And again, if there are questions or anything even afterwards, yeah, you can contact me and I will be glad to cover all your doubts. As Piara mentioned, on the website, you will find not the actual paper, the actual presentation, but the real paper describing all the points that I have covered. So in a real Word document or a PDF document. Okay, that's the end.
Thank you, Danilo, and thank you everyone for joining. I hope you all have a good day.